well, thanks so much for being here. I understand there's some big competition at one of the national technical meetings. So I know that you all do amazing work in CO2 capture here. So what I'm going to talk about is what do you do with all that CO2 that you captured. And so I have every wish for great success on the capture part. So just a quick overview. I'll talk about the big picture briefly. I'll talk about CO2 storage fundamentals, like what needs to happen to make it work. I'll talk about some of the detailed research we do in my lab. So I hate it when you come to these talks and you don't, at the end of the day, get to know, well, what does that person really do when they're in their lab with their students? So I'll talk about that. And then I'll wrap up with a discussion about some of the prospects and challenges for CO2 storage. So the big picture, CCS is CO2 capture and storage. The idea is that you take carbon dioxide from stationary sources and that you scrub the carbon dioxide from the flue gas, and after you've captured it, you then compress it into a form where it's easy to transport, and then again the part that I work on is you pump it deep underground for the purposes of geological storage. So I want to say a little bit about the motivation. Unlike renewable energy, or unlike sort of the natural gas boom that's taking place, really the only motivation for CO2 capture and storage is to deal with the climate challenge and with the climate problem. And I think that's one of the things that makes CCS kind of unique compared to the other technologies. So for example, if you look at solar energy and if you look at wind energy, other motivations in addition to reducing greenhouse gas emissions could be to increase U.S. energy security, as an example, because you have more domestic resources that you can rely on. But really the purposes of CCS are to deal with the climate change problem and the urgent need to begin to reduce CO2 emissions. And just to highlight the urgency, this is just some new data that was obtained this year. This is the extent of the Arctic sea ice. So for a very long time, we've had an enormous ice cap over an ocean in the Arctic, and every year it goes through a cycle. It's basically completely ice covered during the winters, but during the summers, there's some melting of that ice, and then there's what's called the sea ice minimum. And this is sort of the average behavior over the observing time. These are made by satellite observations. And what we saw for the first time in 2007 that was very alarming is the lowest amount of sea ice in the Arctic ever. And now this year, in 2012, it was yet even more reduced. The other thing we're starting to see is that much of the ice that appears is not multi-year ice, it's just ice that's formed over a single year. Lots of things are going to change when the sea ice in the Arctic is gone. There's going to be competition for resources. There are going to be entirely new trade routes established. We're completely changing the ecosystems there. So just one more reason about the urgency of dealing with the problem of climate change, and one more reason why CCS is very, very important. Just a little more of the really astounding data that's starting to be collected. This is some data by Hansen. This was published in PNAS. And what this looks at is the summertime temperature anomalies. So they gathered data from around the world, and they looked at each location, and they were able to basically establish some kind of normal distribution of temperatures around the mean value during the summer. And so then if you look at how this has changed, what we can see is that beginning in the data from the 1950s, so the early window period was from about 1950 to the mid-60s. And what we're now seeing is that the mean temperature is shifting markedly to the right, and that we're also having much more extreme temperatures. So we're 5 sigma deviations around the mean temperatures. And these are the kind of things that we're starting to see all the time now with regard to, for example, the drought in the Midwest this year, and also extremes, the storms that we just saw in the East Coast, and the flooding of New York City was actually all anticipated as recently as about 6 months ago by a very large new study that said that area was a tremendous risk due to rising seas combined with intense storms. So, so just again, I think this is a very important issue. The other thing is that we're going to have a lot more people on this planet. We're heading towards 9 billion people. We have about 7 billion people today. Many people lack access to electricity and cooking fuel. So one can imagine that by the middle of the century, we might need twice as much energy to power the globe as we do today. So it's not like we're in a situation where we can conserve our way out of this issue. We do need more energy, and we in particular need energy sources with low emissions. And of course, that's what CCS is. So that's basically what I said, is, you know, how can we provide 2 times the power while protecting the ecosystems, fresh water, clean air, and so forth. So CCS is often thought of as a technology that's just about coal, and for many years in all the early discussions, people focused on that aspect and how it could contribute to reducing CO2 emissions. But in reality, CCS is applicable to 60% of emissions which come from stationary sources. So in addition to electricity from coal, electricity from gas, oil, probably that's going to go out anyway, cement, refining, natural gas cleanup, and so forth. So CCS is a broadly based technology which can make a lot of contributions. There are many studies using things that are called integrated assessment models, which suggest that 20% of the needed CO2 emissions could be achieved with CCS. So and then just sort of more reasons to consider CCS as a very valuable part of the portfolio. That if we were able to put CO2 capture and storage on a large 1,000 megawatt coal-fired power plant, so one project, this is one big project, is the equivalent to convincing 2.8 million people to change their cars from a car that gets 25 miles per gallon to a car that gets 50 miles per gallon. So in this case, we have a very small number of actors. We can make rapid progress and can make a decision, whereas trying to talk 2.8 million people into doing anything is really challenging. So that's another real benefit, that you get a lot of bang for the buck, so to speak. And a little bit about abatement costs, another reason why CCS is attractive. This is a chart, this was actually prepared by ExxonMobil, looking at the costs of various abatement options, CO2 abatement options, presented in terms of the cost of CO2 avoidance. And so the lowest cost thing we can do, as long as natural gas stays at a low price, is to use the existing gas-fired generation facilities that are basically available today, and some of them are not used to their full capacity, so that's the lowest cost thing. Building new gas plants is also relatively inexpensive. Nuclear, somewhat higher. Wind power, to the extent that it can be, the intermittency issues can be dealt with, can be relatively inexpensive. Here's natural gas, power generation, plus carbon capture and storage, and coal. So you see from this that right away that it looks like gas plus CCS and coal plus CCS are the most expensive options. So one might say, well, why so much focus on this? Well, number one, I hope you reduce the cost of capture, but this doesn't tell you the whole picture. We need to look at all the other abatement issues. So for example, if we were to just focus on conventional engine improvements for the transportation sector, that's actually some of the lowest cost things we can do. Start-stop hybrids, the kind of hybrid car that you can purchase today from many manufacturers. But if we look at all these other options for the transportation sector, they are much more expensive economy-wide then even the CCS options, which are often viewed to be, quote, too expensive. If we really look at the cost of going to ethanol, even second generation ethanol or CNG or other options, they're all significantly more expensive. So from a societal point of view, even what might have the appearance of being costly is still relatively good for the economy. Okay, so that's the big picture pitch, really. Why should we be doing this? And so now I want to talk about the CO2 storage fundamentals. So now we'll look at what some of the options are. We're focusing again on this geological sequestration. So the idea is you can pump carbon dioxide underground into sedimentary rocks. So these are rocks that are formed by erosion of mountains and so forth, and that accumulate in valleys and build up over geologic time periods. And within these sedimentary basins, we can put the carbon dioxide into a depleted oil or gas reservoir. That one is sort of, makes a lot of sense. We've extracted fluids. Why not replace the fluids with carbon dioxide? The second one is if a reservoir is not depleted, it's possible to inject carbon dioxide, and in the process of doing that, you can actually enhance oil recovery. And whilst you can argue that, well, now you're just producing more oil, it actually turns out that by sequestering CO2 while you're producing oil, you actually lower the CO2 intensity of that oil to a significant degree, which is a good thing. The third option is to put CO2 into what are called saline aquifers or saline formations. These are basically just like an oil reservoir or a gas reservoir, except that the fluids in the pore space of the rock are basically salty water. And then finally, there's also the possibility to store CO2 in coal beds, and it's somewhat of a different process. The CO2 actually gets absorbed to the surface of the coal, and in the process of doing that, it can also help desorb methane. So these are the kind of geologic options that are available. And very, very importantly, what we're looking for with regard to sequestering CO2 in an underground formation is basically a pair of two important features. So this is what's called a cross-section. So imagine if I just took an enormous slice through the earth. This one happens to be from sort of the San Francisco Bay to the Sierra Nevada mountains, right, sort of around through Sacramento. And if we took this slice into the earth, what we would notice if we were in a sedimentary basin is that we would have kind of a layer cake geology, where you would have regions where you have sand or sandstone. So these are rocks with relatively large pore spaces, sort of on a 100 micron scale. And then the second thing that we need to have are very fine textured rocks that are deposited, that were originally deposited like on the bottom of the ocean floor. They have very, very fine pores on the sort of scale of nanometers, okay? And this combination of these nanometer scale pores, which basically provide a seal, and these larger scale, 100 microns size pores, we have a storage reservoir. So we're looking for this pair of a seal that overlies a storage reservoir. So that's what we want to find. And there are many places in the earth that have, on the surface of the earth, where you can find these type of systems. About 70% of all known point sources are within several hundred kilometers of a potentially suitable sedimentary basin for storage. Okay. So what's the basic idea now? So I said that what was very important is that we have a seal and a storage reservoir. And this is just a little cartoon that shows you what happens when you would inject carbon dioxide underground. So the green in this picture is the seal, the yellow is the storage reservoir, and we're also now at fairly great depth. We're about 1 kilometer beneath the surface of the earth. Under these circumstances, CO2 is a supercritical fluid. It has a density of about 700 kilograms per cubic meter, so it's about 2/3 the density of the resident fluids in the formation. Okay, so that explains why when we put the carbon dioxide into the storage formation, it wants to float to the top of the structure, and then it ends up trapped beneath the seal. And the seal is basically a membrane which allows the passage of some small amount of water but the interfacial tension between the CO2 and water is sufficiently great that it doesn't have enough pressure to actually penetrate into the seal. So it's actually a permanent sealing mechanism. It's not just a matter of time that literally the CO2 cannot penetrate, except through diffusion in the aqueous phase. So this is the basic idea of what happens when we want to store CO2 underground. And very importantly, we need to really think about what this storage reservoir looks like. And often when people, well, just because we use the word reservoir, people's minds go to the reservoir where we store water, so they picture underground rivers, underground lakes, but in fact it's not like that at all. It's in sandstone rocks, or it could be in carbonate rocks, where basically we have tiny, tiny pores. And this is an image that we collected at the Advanced Light Source. It's a micro X-ray CT tomography. And what it actually shows is the red are the mineral grains. These are primarily quartz. And the green is actually water. And the black dots are carbon dioxide that we've actually pumped into this rock under high pressure. There's a very, very tiny sample, sort of the size of a pencil eraser. And we can actually generate three-dimensional images which allow us to understand how the CO2 distributes itself in the pore space. Here you can see this 100-micron pore space filled with CO2. And a couple of things you'll note that if you look at all the sort of fine pores or pore throats, they're filled with water, meaning that water is the wetting phase. It preferentially attaches itself to the surface. And the black dots are the carbon dioxide are in the bigger pores as the non-wetting fluid. So this is literally what CO2, sequestered CO2, looks like if you could observe it on this microscopic basis. Okay, so that's how it works. So then the question is this a wild, far-fetched idea, or do we in fact know how to do this today? There are 4 geological storage projects that have been in operation beginning in 1996 was the first one. The others started one in 2000, one 2004, and one 2007. Basically, all of them have operated successfully in that no CO2 has breached from the seal or escaped from the reservoir. No one's been hurt. So these operations are done safely. And I just thought I would give you an example of this one. This is probably the most famous of them. This is a project in Norway. It's offshore of Norway, so you can see up in the little map there. So the green is Norway, and that yellow feature is something called the Utsira aquifer. So it's a saline formation. So it's basically sandstone rocks filled with salty water. It happens to be under the sea bottom, which it's just a coincidence. They could have equally well done a project on land. This is a project where they're producing natural gas from a deep subsea formation, and the natural gas has an excess amount of CO2, so that needs to be removed from the natural gas before they can sell it. So it's about 10% CO2, so they need to capture that. Here's their capture unit. They use amine scrubbing technology to remove the CO2. It's a very complex offshore engineering to actually establish this facility. And then you can say, well, why did they do this? Well, Norway has been very progressive with regard to CO2 reduction, emission reductions, and they have a $50 per ton tax. So the company, this is Statoil, either has a choice to pay the tax or to come up with an alternative. So they were the first brave ones to say, well, we're going to sequester this CO2 in the subsea aquifer. So that's shown by the blue region on the top there. So they're injecting near the base of this aquifer. It's buoyant, and so it rises to the top. So that's the little cartoon picture of how CO2 would look. But one of the very important things that they did is they actually acquired a tremendous amount of monitoring data using a technology called seismic imaging, where they basically you propagate acoustic waves through the earth, and when you encounter a region of vastly different contrasting fluid properties, for example, density or compressibility, you get a reflection off that surface. So basically you have a way to image where the carbon dioxide is. When they first got this imaging data, they literally had no idea whether they would be able to see whether carbon dioxide was there or not. So it was really an experiment. And what's shown in this artistic rendering is basically the model for what they think the CO2 actually looks like, that it forms a number of sort of pancake-like layers that are created because within the sandstone aquifer there are lots of actually little tiny layers of low permeability or fine textured rocks. So that's the conceptual drawing that was based on images. So these on the right-hand side here are the seismic images. So the top is the image before there was any CO2 injection. Basically all you can see is the top of the sandstone unit and the bottom. So in 2001, they've been injecting about 5 years, and you see a radically different pattern of the reflections from the subsurface. Those dark blue and red lines, that's the indication where the CO2 is. Here's 2008, so you can see this plume is growing. And here's an example of the difference between the two images between 2008 and 1994. So basically, the really very good news is that the CO2 is very visible using this kind of technique. So these were cross sections. So this is what a map is. So if we were to look down at a map view of what this plume looks like, we can see it from 1999 growing over time. This is a kilometer, so very important. So after about 3 years, we had a 2-kilometer plume, growing eventually to about 5 kilometers and about 1.5 kilometers wide. So, so this was a very important project in that, number one, they did it, and number two, it revealed that the heterogeneity or the variability of these rocks has an enormous impact on the shape and distribution of the CO2 plume. And we'll get back to that in a minute. So, so that's the big idea. Okay, so one can say, well, that project, worked fine, and in fact, there are a couple of other projects that work fine. But if we're going to really do this on a large basis, we need thousands of projects like this. So it's important to develop an overall, really, safety strategy. Maybe one of your safety minutes, a safety strategy for CO2 sequestration. And in 2005, there was an assessment that said, well, could this be done in a replicable way that was safe? And this was sponsored by the IPCC, the Intergovernmental Panel on Climate Change. And basically, the effort concluded that if you select your project in a good site, and you have a monitoring program to track where the CO2 is, and if you have a regulatory system to make sure that, in fact, it is done in a good place and that there's an appropriate monitoring method, a monitoring system, that if you so if you do a project right, that the risks of CO2 storage projects would be no different than sort of conventional oil and gas operations today, and natural gas storage operations today. We have nearly 1,000 natural gas storage projects around the world today that, again, have been operating up to even as long as a century. So it said it will be similar. That doesn't say there's no risk, because clearly, oil and gas production is not without risk. We know that, but it's a tolerable risk. The second thing that they said was that the amount of CO2 you could expect to retain in the subsurface is likely to exceed 99% in 1,000 years. And really, that was just a qualitative statement, sort of a confidence that if you did things right, the CO2 would remain in the ground. So what are the key elements of making sure this is true? Well, at the very, very base of this pyramid is we really need to understand the science. We need to understand the science between a multi-phase flow of CO2 and brine. We need to understand the science of these capillary barriers and these membrane seals in the subsurface. We need to select our sites properly. We need storage engineering. You can't just go out to a site and drill some wells in the ground and pump away. You need to figure out how many wells you should have, where should those wells be, what is your maximum injection pressure, Do you want to do other activities to help manage pressure, for example, extracting brine? So there's a whole field of storage engineering that's emerging. Very important, you need to operate safely, you need monitoring. And the other thing that is now emerging, and it was really after the Gulf Coast oil spill, is that you need to have remediation plans in place, you need to have a contingency plan, so if something goes wrong, you don't need to spend a year or two studying the issues, you have the ability to immediately bring a set of tools and approaches. And this is actually a very active area of research in my group now, is how to do this, regulatory oversight. And then finally, one of the outstanding issues has to do with financial long-term stewardship. Because when the carbon dioxide is put underground there, it's there basically forever unless one day we're clever enough that we can find a way to reuse it. But one has to ask the question, if something goes wrong, who's going to be there? What will there be money to pay for it? And so in fact, there's lots of discussion about creating things like bond funds that would be contributed to by the by the sequestration projects, such that long after the project is finished, that there would be funds available to remedy anything that goes wrong. Okay, so that's kind of CO2 storage in a snapshot. So now I want to talk about what we do in my group that is fun. And so the focus of our work is to understand, will CO2 leak back to the surface? How big will these plumes be? I showed you the Schleifier plume, that was 5 kilometers by 1.5 kilometers, but in general we want reliable methods to predict that. And then we also want to know what will be the long-term fate of CO2 in the storage reservoir. In fact, that there are secondary processes that influence the fate of CO2. CO2, when we have carbonated water, that's CO2, dissolved in water. So CO2 dissolves in the water. Eventually, even the majority of the plume could dissolve. CO2 can also be converted to magnesium carbonates or calcium carbonates. So that there are other chemical and physical processes that are important. So I'm something that's called a reservoir engineer, or sometimes called a hydrogeologist. And those of us who study these problems and seeking to answer those questions, there are a whole number of scales that we can study them on. I showed you some work that we've done on this very, very tiny scale where we look at CO2 in the individual pores. People often study what's called the core scale. You can make laboratory measurements of, for example, average properties. And then there are also people who study the field scale. So in my research group, we started to study this core scale. And we wanted to measure something called relative permeability, which basically says when you have two fluids in the pore space, they have to compete with each other, and we want to understand that competition. And so we did experiments where we co-injected CO2 with water, and what we noticed is that when we actually did, so these are now medical imaging using a medical X-ray CT scanner. What we noticed is that the distribution of carbon dioxide was incredibly heterogeneous. It was so variable. And if you look at the literature, and there was really not very much description of this, that people often thought of this core scale as that's sort of the fundamental sort of homogeneous unit that you can then build more complex models from. So we got really fascinated by this scale, and actually now it's coming to be called something sort of the missing scale problem. And the reason it's called the missing scale problem is that we can certainly develop the fundamental flow equations on the pore scale, solving Navier-Stokes equations, for example, in the scale. But there's no way that we can go directly from this scale to the field scale. So we need an intermediate scale that we can use to have continuum-type representations of the properties of these rocks. So that's what we work on. And the primary tool in our laboratory is something, it's a multi-phase flow visualization laboratory. We have high-pressure pumps, and we have an X-ray CT scanner. We have core holders that replicate the underground conditions, so high pressures, high temperatures. And we designed a system that allows us to do very long experiments. We can do continuous experiments sort of for as long as my graduate students don't sort of go on strike. So anyway, so that's what we do. And and we started looking at lots of different types of rocks. Here's 4 different rocks we've studied. This Maria sandstone is one that is called homogeneous rock, but you can see even from, so this is the porosity now, that's the magnitude of the porosity, still really kind of patchy. Here's another one with laminations in it. Here's a very complex rocks with laminations. Here's a rock where you can actually see remnants of old like drapes from a deposition in a stream channel. Here's like a really complicated rock that's formed by mass loading. And then here's one where we can see nice laminate. Anyway, so it turns out every rock was really heterogeneous, and that first rock that we started to study was no anomaly, and that there was actually a lot to be learned. And so here's an example of one of the experiments. On the top is the porosity, and you see these bands that are subparallel to the core. And when we take carbon dioxide and we inject it into this rock, what we see that there are portions where we have lots of CO2, the green. We also have these portions of the rock where there's almost no CO2. Basically, the lower porosity or finer textured portions of the rock. So we wanted to begin to understand how that works. So like all engineers, we said, well, let's make a model of this. And so we took our rock cores, so these are basically kind of this size right here, and we divided it up into many individual grid cells, and we performed what are called integrated finite difference simulations, basically the mass and energy balance equations. And maybe 60,000 grid elements here. And then we would basically replicate the experiments that we're conducting in the laboratory. And at the time, we really didn't have a good quantitative explanation for all this variability. So we just did a little sensitivity study. The first one said, okay, if all the properties of the rock are constant, the outcome is we have a uniform saturation. The next one we said, okay, let's let the porosity vary, but everything else stays constant, uniform saturation. We said let the porosity and permeability vary. Still, this started to be really surprising. It's like, hey, how do we generate these things? Well, the only way that we could start to replicate what we see is that the capillary pressure curve, or basically the curve that describes the difference between the gas pressure and the water pressure in the pores, had to vary for every little individual pixel. And this was really a big revelation, number one. And number two, this was really hard to simulate, and people just ignored all this stuff. And we're going, well, wow, this fundamental behavior we're observing, we can't ignore it. So that's kind of where we are. So basically we sort of found this missing physics. And then you'd say, well, why are we here in 2012 or 2010, finding some missing physics? And there are really a number of reasons. The first one is that really pushing the imaging to be very quantitative. All of the early imaging had basically been pictures. You could produce interesting pictures, but you couldn't really quantify saturations and so forth. The second thing is that there was no way to determine the permeability of all the individual pixels in the core, because you'd have to destroy the core to do that, and that's impossible. So, because then you couldn't do the experiment. So we developed a new method